Okay, we will start where we stopped from the last session. I think we still need to do C. So from this section A, B, C, D, E, we will do A, B, C for now, and then D, E we will do when we talk about alkenes. So in the last session we talked about A and B. Now let's look at C. How to name C. Okay, so C basically here you can see it is a cyclic structure, and in this cyclic compound there are 5 carbons in the cyclic compound, right? Try to get my pen to work. Okay, 5 carbons, that is, you can name it 1, 2, second carbon here, 3, 4, 5. There are 5 carbons, so that is pentane. And since so it's pent is for the 5 carbons and for the hexane, since it's a cyclic compound, you can say cyclopentane. And there are 2 branches, so this is one branch with 2 carbons, so that is ethyl. And this carbon right here in the second position has 1 carbon group, that is methyl. So ethyl is in 1 position and methyl is in 2. So ethyl goes first and then the methyl because of the alphabetical order. So the name of this would be therefore 1 ethyl, 2 methyl cyclopentane. Okay, so we'll talk about D and E when we cover about the double bonds, how to name the double bonds. Okay, so we'll hold on to that for now. Okay, 1 ethyl, 2 methyl cyclopentane. Okay, constitutional isomers. What are these constitutional isomers? Constitutional, in other names you can also say structural isomers, have the same molecular formula but a different arrangement of the bonded atoms. They have the same formula. If it is C4H10, it will have the same formula, but you will see different arrangement. We call them constitutional or structural isomers. A straight chain alkane may have many branched structural isomers. Structural isomers are different compounds and they have different properties. If the isomers contain the same functional groups, their properties will still be similar. They will have similar properties if they have same functional groups. Like for example, alcohol. So if you have 2 alcohols, constitutional isomers, that behavior similar to the functional groups would become similar. Now here we can see constitutional isomers of C4H10 and C5H12. So this is butane. There are 4 carbons, 1, 2, 3, 4 and 10 hydrogens. And here this one also has 4 carbons, 1, 2, 3, 4 and 10 hydrogens. 3, 4, 7, 10 hydrogens. C4H10 is the molecular formula for both of these, but there is a branch here. The name of that is 2-methylpropanes because the main chain is 3 carbons long and has a 1 methyl group on the second carbon. So 2-methylpropane, and this is butane. You can see that they have 2 different densities. They have different properties. Density 0.579, 0.549, and they also have different boiling points. This one boiling point negative 0.5 and this one even more lower boiling point, negative 11.6. So they have the same molecular formula but their connections are different. So we call them as constitutional or structural isomers. Now pentane, 5 carbons, C5H12. So this is normal pentane. N stand for normal pentane, straight chain pentane. You can put one carbon group as a branch like this. Still it has 5 carbons. You see 1, 2, 3, 4, 5 and 12 hydrogens. The name of this therefore going to be 2-methylbutane because the longest carbon chain is 1, 2, 3, 4 butane. Second carbon has a methyl group. So 2-methylbutane, and this is N-pentane. And you can draw another one where you have the longest chain 3 carbons, and on the central carbon you can put 2 branches. And the way we name is going to be 2,2-dimethylpropane. Okay, so you can see the same formula for all three of these, but the naming is different, the way we draw them is different, so there is different connectivity. And look at the physical properties. Excuse me. The density 0.626, 620, 614. Maybe you will see that the density is little similar, but they are not the same. They are close. But look at the boiling points. 36.1, 27.8, 9.5. The branched one has a low boiling point, and then the normal straight chain one has a higher boiling point. Okay, and so you can see that they have different physical properties. So these ones are called structural or the constitutional isomers. Okay. Dispersion forces and the physical properties of alkane. The physical properties of alkane depend on their dispersion forces. See, these hydrocarbons have only carbon and hydrogen. They are non-polar. Carbon-hydrogen bond electronegativity difference is 0.4. In order for a bond to be polar, it needs to be greater than 0.4. So all of these are non-polar compounds. So the only kind of intermolecular interactions that they carry is the dispersion forces. The bigger or the longer the molecule, the more dispersion forces the molecule will have. So it reflects from these carbon chains. So with 1 carbon, 2 carbons, 3, 4, 5, 6, like that, you can see that their boiling point increases. Meaning when the Wahl forces or the dispersion forces increases, we need to give more energy in order to break those van der Waals forces or the dispersion forces. As a result, their boiling point increases. So methane is a gas, negative 164. So this is the temperature. And you can see these boiling points. Negative 89, negative 42, negative 0.5. So all of these are gases. And then 1, 2, 3, 4, 5, pentane. Pentane boiling point 36. It's a liquid. So these are all liquids. So these are gases because they have very low dispersion forces, very weak dispersion forces. As the molecule get bigger, they have more point of interaction with other molecules. So more dispersion forces, and as a result, the boiling point increases. Chiral molecules. So there are type of molecules called chiral in organic chemistry where we have organic compounds. So let's see what are these chiral compounds. Stereoisomers. Isomers, so you guys know structural isomers or the constitutional isomers. Now we are talking about stereoisomers. Okay, so they are molecules with the same arrangement of atoms but different orientations of groups in space. They have the same arrangement, but in the space they have different orientation. Under that you will find optical isomers. Optical isomers are mirror images of each other that cannot be superimposed. Meaning you can create one molecule, you can create another molecule and that is going to be the mirror image of the first one. So those two compounds, they cannot put one on top of the other one and make identical molecules. We call them as optical isomers. They are mirror images of each other that cannot be superimposed. Now, to become optical isomers that cannot be superimposed, a molecule must be asymmetric. Okay? In order to exist as a pair of optical isomers. So this asymmetric molecule we term as a chiral molecule. How do we identify easily a chiral molecule? You can look up to this point here. Typically, a carbon atom is a chiral center if it is bonded to 4 different groups. For example, let's say you have a carbon here. Carbon can bond to 4 groups, or carbon can form 4 bonds. Let's say the 4 things attached to carbon, let's say A, B, C, D. Like that, all 4 different groups, we can call that carbon is a chiral carbon. Okay, because it has asymmetric center and its mirror image cannot be superimposed. Let's say you have this one, carbon with A, B, C. Is this going to be optical or a chiral molecule? No, because there are 2 groups that are similar. So if you have 4 groups, then we would say that is an optical isomer. For example, let's say carbon has a OH group and then you have a chlorine attached to it. Let's say you have a methyl group and you have an ethyl group, CH2, CH3. If you look at this carbon here, is it a chiral molecule? Yes, it is, because the carbon attached to 4 different groups. So this one is Cl, OH, CH3. So this one is a different group, CH2, CH3, chiral center. Okay. So those are called optical isomers. Analogy for optical isomers. If 2 compounds are mirror image of each other that cannot be superimposed, they are called optical isomers. Excuse me. Just like your left hand and the right hand. So you hold your right hand and this is the mirror image of right hand. Right? But it cannot be superimposed on each other. Just like if you can think of, let's say you have right-handed and then the left-handed gloves. Not the disposable gloves that we wear, but if it is made like the right-handed glove and the left-hand glove, can you put your right-hand glove on the left hand? No, right? So you cannot do like that. Basically, your hands are chiral, so they cannot be superimposed on the other one. Okay, so they are not, your 2 hands are chiral molecules. 2 chiral molecules, so these are the mirror images. Let's say here, this is your carbon compound and this carbon chain has 1, 2, 3, 4, 5, 6 carbon atoms. We are looking at the 3rd carbon. So 3rd carbon has a group. Let's say this is a halogen, chlorine attached to it. And you have another carbon group, CH3. And here you have a carbon group with 2 carbons. Here you have a carbon group with 3 carbons. So let's say this is chlorine, 1 carbon, 2 carbon, 3 carbons. So since this carbon has 4 different groups, this is a chiral center. And then the mirror image of this would be, so this group would be facing this way and this would be towards the other side. And 1, 2, 3, 4, 5. So these are optical isomers of 3-methylhexane. So this is a third carbon, 3-methylhexane, because it's a 6-carbon group. And this is in fact hydrogen, not chlorine. So this is hydrogen, okay? This is a hydrogen atom. 3-methylhexane. And this is the optical isomer of alanine, one of the amino acids. You have a carbon here. It's a chiral center because it has a hydrogen, ammonia group NH2, amine group NH2, and then the carbon group, carbon with 3 hydrogens. And you have another group here, carboxylic acid group, carbon with double bonded oxygen, OH carboxylic group. And this is the mirror image of that. Since it has 4 different groups attached to this carbon, that's a chiral center. So they are optical isomers. We call these chiral compounds are optically active, meaning it rotates the plane of polarized light. If you hit a solution that containing your optically active compound, and you send a plane polarized light, so this optical active compound can rotate the plane of the polarized light. Okay, a compound that rotates the plane of light clockwise is called dextrorotatory, while a compound that rotates the plane of light counterclockwise is called levorotatory. Optical isomers have identical physical properties because they have the same connection. The only difference is how the atom arrange in the space. So they have the identical properties. They have the same density, except that they rotate the plane of polarized light in opposite direction. That is the difference that they carry. In their chemical properties, optical isomers differ only in a chiral or asymmetric environment. In terms of the chemical reactivity, they would behave same, or they would carry similar chemical reactions. But if you put it in another chiral environment, they are going to react differently, which is similar to the binding site of an enzyme. If you look up an enzyme, they provide a chiral environment and therefore distinguishes one optical isomer from another one. The shape of one optical isomer fits the binding site, but the mirror image shape of the other isomer does not. So enzymes has very unique binding sites. It will only able to bind with the chiral compound that it matches with its binding site. So if you take 2 isomers, only one would be able to react. Okay, like the lock and key mechanism of enzymes. So this is the chiral binding site. So only this chiral molecule will be able to fit nicely. If you take the opposite of this one, which is the mirror image, that will not be able to bind because the space how it matches is going to be different. It needs to have the same shape. So many of these drugs that we know of are also chiral molecules. One optical isomer has a certain biological activity while the other either has a different type of activity or none at all. So this is a chiral. This is naproxen. It has a chiral center. So we talk about alkanes. Now we're going to talk about alkenes. Alkenes are hydrocarbons that contain at least one carbon-carbon double bond. We call them as alkenes. They are unsaturated. Remember, the saturated ones are alkanes, that they have all single bonds. Alkenes are unsaturated and have the general formula CnH2n. Alkanes had CnH2n plus 2. Now since you have a double bond, it loses 2 hydrogens. So the formula would be CnH2n. If there are 4 carbons, hydrogens would be 8. If there are 3 carbons, hydrogens would be 6, like that. To name an alkene, the root name is determined by the number of carbon atoms in the longest chain that also contains the double bond. Now in alkane also, we chose the longest carbon that contains the many number of carbons. But here we choose the carbon chain that contains the double bond. Okay. Root name determined by the number of carbon atoms in the longest chain that also contains a double bond. The carbon chain is numbered from the end closer to the double bond. The suffix for alkenes is "-ene". So we always try to give the double bond the lowest number possible. And it ends in "-ene". When you have a double bond in alkenes, it restricts the rotation. Remember, when you have single bonds, they can rotate. But a double bond cannot be rotated. So you have to break a bond if it need to rotate, so that the relative position of the atoms attached to the double bond are fixed. Alkenes may therefore exist as geometric or cis-trans isomers. Another type of isomer that you are learning, geometric or cis-trans isomers, which differ in the orientation of the groups attached to the double bond. And they also have different physical properties. Now, let me show you these geometric isomers of 2-butene. So 2-butene. So this one, but means 4 carbons. 1, 2, 3, 4. 2-butene means 1, 2. So this second carbon has the alkene. So this is butene. You have to represent where the double bond is. So it is at the second position. So the way we name it is 2-butene. So methyl groups are here and the hydrogens are here. So if you draw it in the skeleton formula, it would look like this. And then you can also put this methyl group on this side where the hydrogen is, and put this hydrogen into the methyl position like this. So that give you this formula, right? This is the condensed formula, and then this is the line formula, right? So this we call as cis 2-butane because the 2 methyl groups are on the same side, and the 2 methyl groups are on the opposite side, so we call it as trans 2-butane. And these are called geometric isomers, and their densities are different, also their boiling points different. And this is the space filling model. And this is the condensed and the skeleton formulas. And then comes alkynes. Alkynes are hydrocarbons that contain at least one carbon-carbon triple bond. Alkynes have the general formula CnH2n minus 2, and we are removing 2 more hydrogen, and they are also considered unsaturated carbons. Alkynes are named in the same way as alkenes using the suffix "-ine". If it is pentyne, pentyne, hexyne, butine, propyne, ethyne, ethyne, like that. Okay. Naming hydrocarbons and understanding chirality and geometric isomers. Remember, we did ABC already in the previous time when we talk about the alkane, so we don't have to redo it. It's the same molecules here. Let's look at D and E. So D and E, remember, we try to put our name the alkene where we can get the alkene get the lowest number. Okay, so with that in mind, let's try to number it from this side. 1, 2, 3, 4. There are 5 carbons. So 5 carbons is pent. And since it's an alkene, we have to say pentene, not pentane, alkene, pentane. And we have to say where the double bond is. It's in the first carbon, so we make it when pentene. I made a little mistake. So this has to be pentene. Oh, come on. Pentene. Okay, pentene, not pentane, pentene in the first carbon. And on the third carbon, there is a methyl group. So that is a 3-methyl pentene. 3-methyl pentene. Indicate the chiral center in part D. So which one is the chiral center? Remember how you identify a chiral center? By looking at the carbon that holds 4 different groups. So that is going to be this carbon right here, because it has a hydrogen as one group, and this is one group CH3. This is one group CH2CH3. This is one group CH with double bonded CH2 and the hydrogen on the 4th group. So that's the chiral center. And E. Let's see how to name E. Now for the E, again we try to number it so that the alkene gets the lower number, as well as the branches will get a lower number. So the best side would be this side. 1, 2, 3, 4, 5, 6. So 6 carbons, hex. Alkene, therefore you would have to say hexene. You have to specify where the double bond, it's 3. So that would make it 3-hexene. And you also had to specify where the groups. So on the second carbon you have a methyl. Third carbon you have a methyl. So that will give you 2,3-dimethyl 3-hexene. And it is asking you to draw 2 geometric isomers for part E. Geometric isomers are the cis-trans isomers. Remember, you can put the groups on the same side or the opposite side. So the cis-trans isomers. So this is the double bond. One of the group this carbon carries is ethyl group, and then you have a hydrogen. And on the other carbon, third carbon, you have a methyl group and you have this group here. So how do you find? So the group, the lower group between these two, hydrogen has, you can go by the atomic number or the mass. So hydrogen is 1, carbon is 12. Right, and then it also has 2 hydrogen and another carbon. And the groups attached to this carbon, one is methyl and then the other one is this big group. So between these two, this is the lighter one and this is the heavy one. Always you put the lighter branches on one side, heavy branches on the other side. That will give you cis isomer, 2,3-dimethyl 3-hexane. If you put the lighter ones in the opposite direction, hydrogen this way, methyl this way, and then this is the bigger group between these two, this is the bigger between these two, they are opposite, that is called trans, 2,3-dimethyl 3-hexane. Okay, that's how you would name and draw the 2 geometrical isomers. Maybe we can do benzene in the next session.